Well, we are at the top of the hour, so good morning. Good morning, everyone. Welcome to the NDOT Research Payoff webinar. My name is Lieska Holti, the Research Project Manager here at NDOT. Today's presentation titled Energy Dissipation Optimization for Circular Culverts will be provided by Dr. David Admiral from the University of Nebraska-Lincoln. This project was funded by NDOT and Federal Highway through NDOT Research Program. The champion of this project, who has been also the lead technical advisor, is Julie Ramirez. She is with the Roadway Design Division. You will hear from Julie at the end of the presentation. She will provide her NDOT perspective on this project. So before we start, there are a couple of housekeeping items. We will have time at the end for you to ask questions. But in the meantime, if you want to be able to write your questions on the chat, we will be monitoring the chat, and those will be answered at the end of the presentation. Also, at the end of the presentation, you can also unmute your microphone and ask your questions. And then if you maintain your mic, your camera off, if that would be great, since we're trying to be able to minimize any technical difficulties online. So with that, I will turn it back to Dr. Admiral.
All right. Well, thank you, Lieska. So first, I was told this is the first time that we're doing this with NDOT. I think it's a great thing. I see there's quite a few people online, which is fun for me. It has been over a year since we completed this project, and we've actually started another one that's related to the project. So it's hopefully I'm not too rusty because we just started the other project, but I think we can at least give you a good idea of what we did and what our results were, and maybe some idea of how you can apply this in the field. So I'm going to give a presentation overview first of all, and just talk a little bit about what I'm going to say, and then maybe you can follow along a little better. So I'll give a description of the project first, and describe, why or how we're going to do this and what it's for. And then I'll talk about the model that we used, that we built in the laboratory, and that we collected data in. And then I'll give some model results. And then finally, we'll talk about where do we go from here. And this is mostly a discussion of our ongoing project now that we just started this past summer. So project objective. So our objective for this research was to develop and improve weir-based energy dissipation designs for circular culverts. And really the impetus for this project was the idea of a staggered weir, using a regular weir with a circular culvert and trying to dissipate energy so that downstream you don't have a lot of erosion. And the staggered weir was just a slight variation on a regular weir. I'll talk about what those are if you're unfamiliar with them. But because of this variation, we wanted to make sure that it was behaving properly, that it would do the energy dissipation as good as or better than a full-length weir. And so that was the main reason for this project. So the task that we completed as part of this project was, first of all, we designed and built a test facility, and we used that to collect energy dissipation information in a basin downstream of a broken back culvert. So these broken back culverts, wherever there's a stream crossing in a road, we'll put a culvert in, and where we put those culverts in, sometimes the drop between the upstream side and the downstream side is fairly large, and then we'll put in a broken back culvert to help bring the water down to the lower level without causing excessive erosion. The problem is, of course, whenever you bring water down from a higher level to a lower level, it increases the energy of the flow. We need to reduce that energy. So we built this test facility, and then we tested two types of energy dissipation weirs. We tested the full-length weir, and we tested the staggered weir. And really, both of these were relatively new applications in terms of how they've been used in the past, because most of the time when we've used these types of devices, they have been for rectangular culverts, and now we're applying them to circular culverts. The process involved processing of the data that we collected, and we used this to assess energy dissipation that was associated with each of the configurations. And then, what we get as a result is an equation or a graph that shows these data and how they relate to parameters in the model. And then we can easily scale these results to prototype values, to values for real culverts, so that we can figure out what's the dissipation is going to be in the field, figure out if it's enough so that we're not going to have erosion downstream. So here is a typical broken back culvert. And this is actually a model. It's not a model, it's a prototype design from one of the projects that NDOT had. I think it's down by Deschler, in that area. Maybe it's not that far south. I can't remember which road this is right now. But basically, you see here's where the water comes in. It's on the upstream side of the road. It goes down through this broken back culvert, and then it hits this runout section down here. And then we have this area down here, which is our dissipation basin. And so the length and the slope of these culverts changes with location, or the length of the slope section, and then the angle of it also can change. And so we had to make decisions about what we were going to model, because you can't model everything. And so we tried to decide on a worst case scenario. In the end, it ended up being, I think, probably not the ideal choice, but it was a good choice. It gave us kind of the extreme conditions. I think that ultimately we want to look more at what are some typical conditions, so that we can do better designs for most of these. But having something that was the worst case gives us some idea of, okay, is it going to work in the worst case? So what we're going to focus on is this section down here. This section down here is the runout section and the dissipation section. This part upstream, we can't really model that for every case because it varies so much, like I said. So what we'll try to do is simulate what happens with the flow when it comes in, right at this section, and then how much energy do we reduce the flow by before it goes out. And so this is the part we're modeling right here. We have the dissipation structure here on the downstream end. We have the runout section right here. The blue line represents the water surface. And then there's a blank area here because we're going to try different configurations. We're going to try different types of staggered weirs, different types of full length weirs. And then depending upon what we put in there, the water surface is going to change. You'll see down here that we have a tailwater. So that's holding the water elevation up here at a higher level. And we're going to talk a little bit about that in a second. But we need to predict what the energy losses are going to be between section 1 right here and section 2 on the downstream end. And if we can predict what that is, then we can say, is this a good design or not? Now, I also put the term measure in here because we're going to look at a model. We're actually going to measure what these losses are. And then we can use that to predict in real life what's going to happen. So this is the equation we care about. It's the head loss, or the energy equation, and it shows that the head losses are a function of what comes in minus what goes out. What comes in involves velocity, the bed elevation, and the depth, and what goes out involves the velocity, or the velocity head, the bed elevation, and the outlet depth. We get energy loss even when there is no dissipation device in here. So just so you're aware that we don't actually have to put anything in here, but there will be energy loss. It could be as little as friction loss, but in the cases that we're looking at, we have this runout section is circular, it's cylindrical, and the dissipation structure is rectangular. And just that shift from a circular structure to a rectangular structure causes some energy loss. It's not enough, but it does cause some. By adding devices like this one right here, we try to maximize the loss and minimize the outlet velocity. And if this T value is big, then we've achieved our goal. But if T is really, really small, then we're going to have very high velocities at the outlet. We have to assume that there's no downstream tailwater. That's one thing that Kevin Donahue always said to me, is that we can't assume that there's any tailwater here. And the reason is because a lot of the streams that we have in Nebraska are incised, And so we could have a drop here that's significant. We have to make it so that this dissipation structure does the energy loss as much as possible, and that we're not relying on the tailwater to do the energy dissipation, because we can't expect the tailwater to always be there. All right, so let's look at the devices that we tested. First of all, we looked at a full-length weir, and we looked at 4 different iterations of this full-length weir. They were different heights. So we had a smaller one, and then we had a mid-sized one, and then a taller one. I think it was ranged to 1/8 of the diameter of the culvert, to 1/4, to 1/2. Oh, and 3/8 of the diameter of the culvert was used. So we went up to half of the height of the culvert for this full-length weir. We did the same thing for the staggered weir. So this is your first look at a staggered weir. We've got the central baffle right here, and then we've got these side baffles to reduce flow around. And the idea behind this was to prevent sediment buildup upstream of this baffle. So by creating a gap here, you could allow sediment through. And at the same time, we wanted to have the effect of the full-length weir. And so that's what we're testing for. So here is just to give you an example. This is one that has been built in the field, and you can see the side baffles down here, and then the central baffle right here. And just for scale, there's someone's foot right here. This is about 15 feet long, and I believe it's about 6 feet wide, this one. They do vary in size a little bit. So yeah. So weirs and sills, if you look, we have 5 different cases here. So this is for a rectangular channel, but we can get similar things for a circular channel. But you see the flow coming off here, and then we have this sill right here. So a weir is just when it's fully submerged. A sill is when it's not quite as submerged. But anyway, so here we have the weir flow or the sill flow. And these cases this is called an A-type jump. And this next one right down here is a B-type jump. And then we have a minimum B jump. And then we have what's called a C jump. And then we have a wave flow. And the wave flow is really not ideal. We find that that's what's happening in some of our cases, because what leads to these other types of jumps is basically tailwater. And like I said before, we're trying to do this without tailwater. And so we're going to get flows that are more like KC, the wave type flow. In any case, we still want to reduce this flow energy as much as possible. And it would be great if we could get subcritical flow. We haven't been able to achieve that in such short distances, but maybe with the new project, we'll be able to do that. I'm hoping. This is our test facility layout. So this is what's in our lab. I don't really have anything here to show you scale, but to give you some idea, this pipe right here in the testing section is 5 feet long. So it's a fairly large setup. This is our storage tank down here. That's basically where we store our water all the time, even when we're not running the experiment. And our pump in that can provide up to 3 cubic feet per second, which is about 180 pounds of water every second. So it's a pretty significant flow. It's nothing what can be supplied at Colorado, where they have a huge reservoir to supply the flow, but it's a significant amount of flow. And then we have this constant head tank right here. And the whole purpose of this is to act as like a water tower. And a water tower, the reason it's there is to keep pressures constant in the lines. And that's what we want to do, is keep pressure in this supply line constant. And if we can do that at any flow, then we can control our flows really accurately and not have to worry about the flow changing during the middle of the experiment, because pumps are actually quite unsteady. They're not very consistent. But if we provide a water tower, we'll call it, then we can provide very consistent flow at a very constant pressure, and then we know if things aren't changing. So we have a butterfly valve to control the flow if we want to do a high flow or a low flow. Then we have a head box that just kind of steadies out the flow. And then right here is our drop structure. And then this is a runout section. Here's the dissipation base. And this is where we're going to put our test devices that we're going to test out. And then we have this tail box here. And the tail box is, the purpose of that tail box is just to act as a way to collect the water and send it back to a weir where we can measure what the flow rate is. And yeah, that's the layout. So here's a side view of just the testing section. Let me go back a second. here. So I'm gonna this highlighted area right here is the testing section, this dashed area, and that's what we're gonna look at. And that's this right here. So here's our tail box. Here is our head box. And my grad student drew this in AutoCAD. I thought she did a great job because it's really very representative of what we produced in the lab. I kind of wish I'd had her do the dissipation basin in here, but I didn't have that in there. So here's the runout section. And let's take a closer look at this. So this is after we started building it. This is during the construction process. And I like this picture because it kind of shows you all of the things at once. Here is the dissipation basin. This is where we're going to mount our structures. You'll see that we have these sloped or these cutout walls. We actually put rectangular walls in later just because we thought it was more representative than doing this. So it's a little different. But here we have the runout section. Here's the drop structure. Here's the head tank. And this part right here is actually connected to this in the next step. So here is our drop structure. Just a little closer look at that. There are actually little piezometers in the bottom of this that you can't see. They're not in there yet in this picture, but they're pressure taps for measuring depth. We have the same thing throughout. Here's another look at it from the side. And then this is after we put it all together. So now you can see the tailwater basin's in place. Here's our dissipation basin. Here's our runout section, and we've got water coming out of this. And just to give you some idea what this looks like, I've got this little video here. So here's the flow coming out of the runout section. And what you can see in this picture too is there's these little gray areas on the bottom. That's just because that's where our pressure taps are. So we're measuring pressure there in those locations. These are just bolts. They don't stick out in the flow at all, but because the water's so clear, you can see them real easily. So this is all flat and flush, and you can see that those little piezometers, they go all the way upstream. So we can measure depth anywhere. As it turns out, the velocities are so high and so turbulent, they don't work all that great. So they worked, but not perfectly for the flows that we did. And so we had other methods of measuring depth as well. So here's a side view to show you what it's like in the runout section. And so I'm going to run the video here. So you can see that there's a big hydraulic jump right here inside of this culvert right here. And in a flow without a tailwater, you wouldn't see this here. So what's happening is we have backed up the flow in this tailwater tank enough that we get a hydraulic jump in here. Now, what you hope to have is that your dissipation structures create that hydraulic jump. The problem is when you create this hydraulic jump, you're backing up the flow. So you reduce the energy somewhat, but by backing up the flow, you create additional potential energy, which once it gets past the dissipation structures can lead to higher velocities. And that's one of the things that we saw for our higher weirs, and I'll show you that when we get to the results. All right, so just to kind of ram this home, this is our original prototype here. The part that we're modeling is this part right here, down here. And so I've kind of given you an idealized structure here. So we've got the runout section, the testing basin, we've got the drop structure and the head tank. The drop structure we have is a little bit shorter than the one I have shown here, but it's basically the same idea. In the original model that we have a gate so that we can control what the velocities are coming in here. The gate didn't work very well. We're redesigning it for our new project so that we don't have the same issues. All right, so flow measurement, mentioned earlier, we have a V-notch weir. This is for measuring the flow rate. And I just like to show this video because it's fun to watch. So anyway, we use this to measure discharge, and the way we measure it is we just measure the depth in this tank upstream, and there are known relations between the angle of this weir, the height of the flow behind the weir, and the flow rate. And these are used all the time in canals and stuff to measure irrigation flow rates. This one right here is a very sharp angle. The reason for that is because we want really high accuracies, and so that's why it's designed this way. All right, so let's talk a little bit about our measurements in the model because we'll have to measure energy at the inlet and outlet. I showed you this energy equation earlier. We need to measure all the values in this equation. The Z1 and the Z2 actually are not that important because Z1 and Z2 are the same. Those are the bed elevation, and they're the same at section 1 right here and at the outlet. So they don't matter. But what does matter is D, the depth at the inlet. And unfortunately, this is less accurate to measure in a high velocity flow because the depths are much smaller. And so it's one of the places where we've been working to try to improve the measurements of this D value. And there are other ways to calculate D indirectly. And so we do apply some of these to see what works best. With V1, to get the velocity at section 1, there's a couple of ways to get this. One way to get this is to measure D, and then we already have, I talked about measuring the discharge. I've already measured the discharge. So if I measure the depth and I know what the shape of this flow area is, which it's just a circular culvert, I can get the cross-sectional area, and then I can just do Q over A. And this is how you would do it if you are um, if you're doing an analysis of it in a spreadsheet or something like that, because our theoretical values of depth are quite good. But the measurements in the lab are a little bit different, and it can be hard to measure this depth. And so instead, what we can do is we can also measure the velocity at this point. And I'll show you how we do this. We can measure the velocity at the position, and then we can get V1. And this is really accurate if we know the velocity distribution well. So we use this information about what is the velocity like inside the culvert. And if you know how the velocity relates, the average velocity relates to this point velocity, then we can get a really good estimate of this. And this is one of the ways that we do it. Alpha 1, to get that, really the only way we can do this is from literature. That's the most feasible way to get this velocity correction factor. And then at the downstream section, we have a different section. So the upstream one's circular, the downstream one is actually rectangular. And so again, Z2 and Z1 cancel out, so we don't have to worry about those. But T is typically quite shallow, and it's turbulent. And so we could measure this directly, and we did start out trying to do it this way, but it was difficult to measure because it was so turbulent and so shallow. And we used point gauges, we used piezometers, really hard to measure it accurately. To give you some ideas, some of the depths in this are only about 1 centimeter. That's different than in the culvert where it's a bit deeper. It might only be 1 centimeter deep. And if it's only 1 centimeter deep and your measurement accuracy is plus or minus 2 or 3 millimeters, you might have 30% error on this, and that's pretty significant. And so instead, what we did here was we measured velocities. So we measured the velocities across the channel, and then we could calculate from our known discharge, we could calculate what the depth was, and the velocity distribution, we used something from the literature, and we could get the depth indirectly instead of directly measuring the depth. Velocity, again, there's 2 ways to get this. We can measure the depth and then use the shape of the outlet section to get cross-sectional flow area, and then use Q over A. That's accurate if T is accurate. And then we can also measure velocity at a point like we did for the depth, and get V2 indirect. We can get velocity a little bit more directly. We decided that the second way down here was actually better. And the reason why the second way is better is because most of the energy that we have at this location is contained by the velocity of the flow and not by the depth. And since this is the energy equation, this term, if it's bigger than this term, this is the one we want to get the most accurately if we have to make a choice. All right, again, alpha 2 literature information is really the most feasible way to get this. Instrumentation, so we wanted to measure velocity and depth. So here's velocity measurement. We use these Prandtl tubes, and we had 2 Prandtl tubes in the upstream runout section. Really only P2 is useful to us. P1 was more just in case we needed it, but we didn't. And then down here we have 3 Prandtl tubes. We have one on the left side, one on the right side, and one in the center line. And those give us a much more accurate measurement. So you can see those 3 right down here. Here are the 3 Prandtl tubes that we used. And then we have these stilling basins. And remember, with a Prandtl tube, you have to measure both the static pressure and the stagnation pressure. And so each one of these stilling basins, there's 2 of them for each Prandtl tube. And then we look and we see how high the water level gets up in here. And if we measure the difference between static and stagnation pressure this way, we can get the velocity. Now, to measure it with these would be hard to do. These are really just basically stilling wells, but then we connect these to electronic manometers or digital manometers, and we can get very accurate velocities that way. And then we use the energy equation to get head losses. All right, so for using the upstream panel tube, I just wanted to show you this in a little bit more detail. So we have this velocity distribution right here. We're going to use these, instead of using point gauges, we'll probably use a Prandtl tube, but most of the time we use both and just compare them. And then the Prandtl tube is always a fixed distance from the bed, and so we need to know this velocity distribution in order to convert this to a bulk average velocity. And all right, so this is another velocity distribution I'm showing you. And if you look at this distribution, you'll see on the x-axis, this says this U over UB. So it gives you the velocity at a location in a circular pipe related to the bulk average velocity. So we just do a correction. We figure out what the depth of the Prandtl tube is, and then using that, we come up with a correction. There is some literature that allows us to assess bulk average velocity. And the conditions aren't perfect for this purpose. But it's the best we can do. The biggest problem that we faced was most of the literature is for low Froude numbers, and since our Froude numbers are relatively high, we had to make some extrapolation there to do it. We don't think it's a huge amount of error, but it's just another possible source of error. So just to remind you, these are the things we're testing. I'm going to start getting into the results now. And so we've got on the right the bulk, the staggered weir, and on the left we've got the full length weir. And we'll just compare these side by side. So first of all, we're going to look at just outlet depth versus discharge. And you'll see, like I mentioned before, some of our outlet depths are really low. These open squares right here are the outlet depths that are associated with having no weir at all. So it's before we put any weirs in at all. We did a bunch of tests, and we did this over a range of discharges, all the way from 0.015 to about 0.055 CFS. But I want you to know that this line right here, this dashed line here, is basically, that shows where the tailwater starts to influence the flow. So I mentioned earlier, we don't really want tailwater to influence our results. Everything to the right of this is where the flow was high enough that in our tailwater tank, the water depth got up high enough that it was starting to affect the flow. And so it didn't affect it very much for this first set of points, but for the last set, you can see there's a strong effect of that tailwater on the flow. And so that's another thing we're fixing for this next round, this phase 2 study, is we're making it so our tailwater basin can handle a lot more flow so that we can cover a wider range of conditions. But you'll also see from here that this is basically the lowest amount of outlet depth. And then as we add higher and higher weirs, you get higher and higher outlet depth. And that's basically because you're having more and more energy loss. And the best case that we had was these dark blue squares. And the dark blue squares are when the staggered weir is half of the size of the culvert. So if our culvert is 48-inch diameter or 4-foot diameter culvert, then the best staggered weir we could use would be about half that size. It doesn't look like much of a change, but that's because a lot of the energy is contained in the velocities, and it actually is quite a significant change in energy. Now, this right here, this dashed line up here shows critical depth. Critical depth is basically the best we can do. If we could get the flow up to critical depth, that would be ideal. But that's pretty hard to get it that close because of the way that critical depth, energy, and depth are related. Still, there is room for improvement. So this is maybe a little bit better representation of how well the weirs perform. So this E critical is the specific energy at critical depth. And you see that it's actually not that much below what it is for the highest staggered weir. So in this case, we want to make these go down as close as we can to this line. And we'd love to be able to go below. That's not physically possible. but if we could get down to the line, it'd be good. What you'll also see is over here, we got down to the line. Hey, that's great. The problem is the reason we're down to the line is because there's tailwater and it's creating its own hydraulic jump. And so really the dissipation devices aren't really doing anything in this case. What's doing is the tailwater. It's not helping us. So in these areas, these are the ones that tell us what's going well. And you can see that this is when there's nothing in place. And as we move down, as we get higher and higher weirs, we get more and more dissipation. But I also want to show you one additional thing, and that is for the full length weir. So the full length weir right here, you'll see that there's yellow, green, blue. And so we've got, if you look down here, the green circles are actually below the blue circles, and the blue circles represent a higher weir. So what's happening here is we are getting a weir that's higher is causing less dissipation of energy. It seems odd that that would be the case, but really what's happening is that with this higher weir, we're backing up the flow, we're creating potential energy. When the water starts flowing over that top of that weir, it picks that energy back up as kinetic energy. And so actually in this case, having the higher weir is a bad idea. That's not the case for the staggered weir, because with the staggered weir, what happens is that even though the weir gets higher, there's these gaps between the weirs that cause it so that the flow isn't forced back as much. So it doesn't create this potential energy behind the weir. That's a good thing. All right, another picture right here, we have additive energy loss. This is just tells us how much energy do these dissipation devices remove in addition to what's already removed by the dissipation structure itself. So this added energy dissipation is beyond what's provided by the expansion alone. Remember that this thing's going from a circular culvert to a rectangular culvert. Just that alone takes away some energy. And so you can see that, again, there's, the lowest weirs don't remove as much energy as the highest weirs. The staggered weirs do better than the full length weirs. And you'll see that it increases as you go up here. This is the most energy we can remove before we get to critical depth. And so we're getting pretty close up there, but there's still some room for improvement here. And yeah. This DE max, like I said, that's the maximum additional reduction possible beyond that provided by the expansion. Total energy reduction. So in this case, delta E is the difference between the energy inside the culvert and at the outlet of the culvert. How much energy has been dissipated in total. And you'll see that, again, the staggered weir does the best, the squares. But there are, at the low discharges, this is kind of interesting, at the lower discharges, the full length weir actually does a little bit better. And in fact, it's not this the blue full length weir, it's the yellow one that does better. And the reason for that is because at the lower flow rates, the depth is a lot lower, and so those lower weirs can do a pretty good job. This E1 is based on 2 depth readings in the culvert and the Coriolis coefficient of 1.25. Just so you know, E2 is based on the outlet velocity readings and a Coriolis coefficient of 1.15. One of the things that we did notice too was that these lower weirs for the full length weir and for the staggered weir, they're not very effective. And the reason they're not very effective is you get skimming. What happens is the water just skims over the top of the weir. So they would not be ideal to use those. The higher weirs are actually quite effective at producing jumps. And then I have some dimensionless results here. These didn't turn out as well as I would have liked. We're going to shoot for better in our second phase. But they do show that, again, that the staggered weir works really well at the upper end, this 4D/8, where it's half the size, half the diameter of the culvert. The reason these dimensionless energy changes are useful is because I can use these same results in a prototype as what I use in the model. So I can take these results directly, bring them to the prototype in the field, and figure out what the energy loss is going to be, and use that to figure out head losses and the outlet depths and so on. And then for the full length weir, we have a similar diagram right here. So here's the runout Froude number, and again, dimensionless energy change. One of the things that the reasons that these results are not as good as I really want them to be is because the runout Froude numbers don't change very much. So remember that the discharge is changing from about 0.01 cubic foot per second to about, I think it was 0.05. No, I got that wrong. It's 0.1 to 0.5 cubic feet per second. So the discharge is changing a lot from between these tests, but the runout Froude number doesn't change very much. And the reason is because the Froude number is based on the velocity in the numerator and the depth in the denominator. And as the depth goes up, the velocity goes up, so the Froude number stays about the same. And this is where our new design, what we're going to do is we're going to have a lot less slope in the drop section, and that will allow us to adjust the runout Froude number a lot more. That's our goal, is to get a much wider range so that this works out better. Again, there's just not a lot of variation here. It's only from 3.8 to 4.4, and what's that, about a 20% difference between the highest and the lowest value of Froude number. Wrong direction. Sorry. So here's dimensionless results. I'm going the wrong direction. All right. So here's dimensionless outlet energy related to the critical value. So this is as low as we can possibly get it. And this is, again, the staggered weir. This is the lowest value we got when it was half the size of the diameter of the culvert. So there's this room for improvement here. And same thing here, we've got this room for improvement. Again, that's where we're going to have this phase 2. I'll talk about that in a second. So our conclusions. First of all, the piezometers didn't appear to be as accurate in highly 3D flows with significant aeration. And the point gauge measurements are more reliable in that case. Didn't really talk about this very much, but we also had, so we measured depth using piezometers. We also used point gauges, which are down from the top. So you can measure from the bottom or you can measure from the top. We did both, and we found the point gauge measurements were better. Measuring exit velocity was more accurate than measuring exit depth. And so we used those the Prandtl tubes that I showed you to do this. Energy dissipation performance improved with weir height, and the performance improvements were significant for low weir heights, but they weren't as significant for the large weir heights. Both the staggered weir and the full weir were effective for dissipating energy, in addition to the energy dissipated by the expansion alone. But the staggered weir was more effective than the full-length weir, especially when we started talking about the higher depths, even though their effectiveness is similar. And then for the full weir, the optimal height of the heights tested was about 3d/8. For the staggered weir, it was about 4d/8, but it's actually only slightly better than the height of 3d/8 for the entire test range. And what we get is that for the highest velocities, the highest heights work best, but for the lower velocities, the lower heights work better. And so a couple additional conclusions. I would say that I would avoid weir heights that were less than 3d/8 within the range of testing conditions. And the main reason for this is that the flow skims over the weir in these cases. And a second conclusion is that the optimal weir height within the range of testing conditions was about 4d/8 for the staggered weir, so about half the diameter of the culvert. And it was about 3d/8. I'm sorry, 4d/8. Oh, I got these mixed up. Yeah, no, that's right. Staggered, it was 4d/8. For full, it was 3d/8. And then there was an issue with the higher full-length weirs, and that was that the flow was backing up behind the weir, and that stored potential energy, and that becomes kinetic energy. And I've kind of drawn this for you in this picture down here. So you have the weir down here, and if this backs up the flow a lot, then this depth up here, this HW, gets bigger and bigger and bigger. And as that gets bigger, higher up, then it gets converted back into kinetic energy down here, and you have really high velocities down here in that case. So in some cases, it's actually better to have a lower weir than a higher weir. Let's talk about where we're going with this. So the phase 2 part of this project, and we just started this summer. So it's most of what we're doing right now is in the building phase. But we want to kind of explore the limitations of the previous project, and this will help us to build a better project. First one was that the maximum discharge was limited by the tailwater depth. I showed you those dashed lines, the vertical dashed lines, in a lot of those diagrams that were saying, hey, any of the data to the right of this line, not very good because we've got tailwater that's backing up the flow. And what's happening is we're not really measuring the energy dissipation of the device. We're measuring the energy dissipation of the device plus a hydraulic jump caused by the tailwater. So we're doing a couple of things to improve this, to increase the maximum discharge, reduce the tailwaters at the outlet. I'll talk about this in a second. A second thing is that the break-in slope that we had a really high slope of, I think it was 15 degrees was the slope of the drop, and that was to simulate the worst case scenario. But there were problems with that. One of the things was it caused oscillations in the runout section. Another thing it led to was really high Froude numbers, and that made it so that the runout energy was really not easily controlled. Even for the lowest flow rates that we had, our Froude numbers were really high. So we'd like to get down to 2 if we can. And so there's a couple of things that we're going to do to fix that. And then dissipation structure optimization is the second goal of this phase 2 project. It'd be really beneficial to optimize the positions of the staggered weir baffles, figure out where is the best place to locate them within this dissipation basin. And then also, can we vary the heights of the central and the side baffles? So we'll check out that as well. If we change the central baffle to be tall and the side baffles to be short, or change their arrangement where they are in the system, how does that impact how the thing behaves? So our objective then is to optimize the staggered weirs so that it maximizes the flow energy dissipation. And then our goals are going to be to extend the range of applicability of the staggered weir by modifying the testing facility. And that allows us to get a wider range of Froude numbers and inlet conditions. And then we'll optimize the geometry of the staggered weir. So here's the first thing we're working on right now, and we've actually already dismantled everything here, and we've started raising the tank. And so this tailwater basin is a lot higher. That will allow more flow to come out of this tailwater basin because there's going to be more head pushing the flow out. But also, we're going to move this floor of this dissipation basin up higher so that any tailwater that forms in this tail box won't have any effect on the flows. The other thing it does by raising this tail box is that we're making this flatter. So you'll see that this drop section has a much lower angle. And we have a sluice gate in here right here. We're going to redesign that so that it works a lot better with this system and we can control the flows a lot better. So we're going to increase the height of the tailwater tank, and we're going to reduce the drop between the head tank and the tailwater tank. What effects will this adjustment have? Well, the first thing is we're going to remove this, right? We're not going to have to worry about this section. These here, we're going to be able to do these really high flow rates of 0.05 cubic meters per second. We're going to be able to do those really high flow rates and not have to worry about tailwater. So that's the first thing. And then the second thing is that we're going to be able to do a much wider range of runout Froude numbers. We're going to hopefully get down to the 3.6 to the 3 and maybe even down to the 2s here for runout Froude. So kind of simulating what you'll see in the field for all of your different designs. The other thing is this adjustable geometry. So here we have the original structure. We're going to be able to move this. We're going to be able to move the central baffle and the side baffles here. And then lastly, we're going to be able to change the height of the side baffles so that they're different than the central baffle. And the adjustment effects that this will have is that hopefully we'll be able to get down into this area right here and get these staggered weir data down closer to this line. Hopefully in a point where it's subcritical flow, so we have nice high tailwater depths. I'll show you a quick discussion of the progress so far. The facility, the tailwater tank is ready to be raised in height. We actually have it, all of the mounts made and everything. I've been waiting to raise it because we're waiting on some PVC pipe and some 3D printed parts that we don't have yet. And then we'll raise that tank. In the meantime, we're working on the dissipation basin, and the adjustments are really nearing completion. I'm going to show you a little video in a second here, but I have this really fantastic graduate student working on this, and he's made these so that we can adjust the positions of the baffles while there is flow in the flume, which is a real challenge to do, by the way. But I'll show you what he's created. I'm going to go ahead and I think this is the end of this presentation. So let me go ahead and open up that video. So this is a video that shows the movement of these baffles. We're looking down from above, and you can see there's a little lead screw down here. And he's adjusting this by turning the lead screw. Well, that's the side baffles. And now we can also adjust the central baffle here. So he's going to adjust that next. We still have to do a little bit of work on this, but you can see that he can adjust the position in the streamwise direction of these baffles. And the nice thing is, like I said, we could do this remotely with flow in the tank. So you can't see it very well in this picture right here, but the bottom here of this is plexiglass, so it's clear. And so when you see the lead screw here, that's actually under the plexiglass, and this is above the plexiglass. This metal piece here is below the plexiglass. So the water actually will flow above the plexiglass. There will be coverings for these slots right here that prevent water from going through the slots. But the idea is, can we adjust this in real time? If we adjust this while there's flow in the tank, we can optimize the position really accurately. Then when we find the optimal position, we can remove this and replace it with fixed values of the baffles and get a detailed set of data. So I will stop there, and I'll just ask if there's any questions.
Doctor, we do have on the chat a question. Are circular covers typically smooth like your experimental structure? I will have guessed that the covers for the setup are typically corrugated metal pipe.
Yeah, so there are two types of pipes that are used in these structures. There's reinforced concrete pipe, so RCP, and there's corrugated. So we are not simulating the corrugated, the RCP. We're simulating the RCP, right, the reinforced concrete pipe. And actually the roughnesses are, pretty reasonably similar for those. That said, the roughness of the pipe actually doesn't matter very much for the short distances we're talking about. What matters the most is there being a jump that's being induced by these dissipation structures? So that's the thing that induces it the most.
Can I add something to that, Dr. Admiral?
Yeah.
I wanted to touch a little bit on that as well, but with our energy dissipation, we typically like to try to put in metal pipe because that's our first option to slow down the water. Unfortunately, when we get to some of the construction methods, we are limited to just jacking pipe, and that's where we get into more of the concrete. But like Dr. Admiral said, that roughness doesn't matter 100% in this
Now,
case.
what I will add to that is that in the case of concrete pipe or RCP, that would be the worst case, right? So you would get the most velocity from your drop if you have smooth concrete pipe. If you have the corrugated pipe, then the roughness is quite a bit more, and you will get more energy losses by the time it gets to the runout section. So it actually helps you a little bit if you design with your baffle structures with your RCP in mind. Then it will probably be better than it will be, once you put in the corrugated pipe.
Thank you.
One more thing. I want to add that I originally had hoped that we could do something with corrugated pipe, but it is really, really hard to come up with a physical model of corrugated pipe because scaling things down is not a very easy thing to do. So, yeah.
Thank you. So next question we have is, if the center baffle was converted to the wedge, that it changed the outcome?
If the center baffle was converted to a wedge,
Yeah, that it changed the outcome?
yeah, I mean, so geometry wise, so wedge might be different things. Um, it could be a wedge where you're pushing the water off to the side. Um, it could be one where the wedge is a vertical wedge where there's a slope on the front end. Typically with baffles, you want them to have a vertical front face. That's, at least from the literature, that is the most effective type of baffle. Whether we want to push the water towards the edge, that might actually be a good idea. I have thought about a bunch of different ideas about how we could improve the baffles the way they are. Um, I think having a flat face on the front is a good idea. Um, there are some designs where the water is kind of curled back around to try to push the water backwards. I'm not sure that's really hard to construct that sort of thing. I'm not sure it's worth it in this case. But I think that one of the questions I want to answer as part of this phase two is, if we make this baffle narrower and then we have more of them, would that help our results? Because then you have more flow area in between, and it doesn't push the water back as much. It just diverts it, dissipates the energy, and then hopefully moves downstream at a slow velocity. I'm not sure how to answer the question. There are a lot of different configurations that we could explore. I'm not sure. We didn't try doing a wedge, so I can't tell you. But I like thinking outside the box. I like that.
Any other questions?
Dr. Admiral, with this research, we had pretty narrow fruit numbers. So the following research, we were hoping to get a larger range of fruit numbers, but do you know if we'll actually see that when we get done with phase two?
Yeah. So as I showed you, we're raising that tailwater tank, and a
Hmm.
big part of our problems was that really high slope limited us to really high Froude numbers. In fact, if we had installed that gate and it had worked properly, and we had made adjustments to make it work properly, we would have just gotten higher Froude numbers. That's all we would have gotten by lowering the drop, by reducing it. I've already done some calculations. We can get much lower Froude numbers. And then if we want to get to higher Froude numbers, all we need to do is we could add a gate, or we can extend the pipe farther upstream into the tank. And by extending that stream farther upstream, by extending the pipe farther upstream into the head tank, we force the water level in the head tank higher. That will give us higher energy as well. So there's a number of ways we can increase Froude number. Very difficult to reduce it. And so by making a much lower slope, we will have much lower Froude numbers. Yeah. So I'm excited about that. In fact, I told my grad student, we have to make this very flexible this time, because I want to make sure that if it doesn't work the first time around, that we can make a quick adjustment and make it work. And one of the things we're trying, I haven't had the chance to get it tried out because the printer upstairs is broken, but we're 3D printing some of the parts so that we can adjust things like the inlet slope by 3D printing a new connection between the runout section and the drop. And so I'm hopeful that works well. If not, we're gonna have to manufacture them by hand, and that's a lot harder.
We have another question in the chat. Would you look at the clogging of the baffles and adverse effects?
No, it's a really good question, because I know that these do get clogged, but certainly it won't be as bad as the full length weir. The clogging part is kind of hard to do from a modeling perspective. You can scale down some debris, but then you have to decide, what are you going to use for debris. So are we talking about just sedimentation? This thing will, the baffles, the staggered weir, or the baffles, they are not going to sediment as much as a full-length weirwood by any means. In fact, that's one of the reasons we designed it this way. But there's always a risk that upstream you have like corn stubble, or you could have branches or something like that. And the reality is that there's no way to get rid of that. That happens at every baffle I've ever seen. There's always some way for these to get removed. So I think the way you deal with this is you have to periodically service these and remove debris if there's debris in them.
Thank you. We do have another question. What about using two sets of baffles, maybe of various height between the two sets?
Yeah, that's actually what we're talking about doing. That was one of the things I showed in one of the slides. Let me see if I can pull it back up again. I probably didn't present it very well. If you look at the right-handmost picture here, you'll see that there's these orange lines. Those represent the height where they're the same height as the central baffle. And the ones on the side here are shorter. So that's one of the things we want to try is having a larger one in the middle, shorter ones on the sides, because the larger one will absorb most of the energy and dissipate it. And then the shorter ones will help to kind of disperse the flow a little bit, absorb a little bit more energy, but not force the water to be at a higher elevation, end up with a higher elevation at the outlet. That's a great insight, yeah, to think about that sort of thing, I think. If we could use multiple sets of baffles, so this is just two sets. If you use maybe three sets, maybe we could do even better. I don't know. We may try that sort of thing. Keep in mind, though, that every time you add a set of baffles, that increases construction costs, makes it a little more difficult to make.
Julie, what about in your perspective? This basically this is the phase 2 of the research in this concept. So could you elaborate a little bit more of the envisioning on how when we do research and how you basically will in the future will be implementing or just basically getting ahead on just getting the benefit of for the outcome of this research?
Absolutely. When we first started this project, the baffle research was originally done in early 2000s with Dr. Hotchkiss. And when I read the paper on that, it was only applicable to broken back boxes. But we do have a need for energy dissipation. So we did apply the baffle design to round pipe, but with Dr. Admiral at the university and the ability to use the lab, we felt like this was a good opportunity to start taking a look at round pipe. And just from his geometry, like when you go from a round pipe to that box, we have energy loss there. And then we're trying to get the hydraulic jump to dissipate the energy even further. Once we got through this first round of research, we found out, hey, we probably need to take a look at a couple more things further. So it's really exciting to continue on to the second phase, and we are going to implement it because we are implementing it now, but we're going to use the research that we have to understand more how the energy is being dissipated, how we get that hydraulic jump, and then use it out in the field today. So we'll see what happens with this research. And one thing that Dr. Admiral has done, and he's given us tours of the lab, and then even with the remodel of the whole engineering campus down at the university, there is now a glass kind of an overlook area that you can see the lab from above. So it's really cool. It's a little different than when I went to school. So like I said, I'm pretty excited. I'm a little biased, but we're excited to see what the results will show.
Yeah, the glass that's up above there makes it a little bit like a fishbowl. So don't knock on the glass, distract the fish when we're doing our work. But but yeah, so in what Julie said, I actually wanted to mention too that I intend to invite people over to come see it because it's always fun to show the lab, and that would involve people from NDOT. And so If you are interested in coming seeing this when we get it running, it'll probably be in the spring or the summer is when we can have you over. Then just talk to Julie or something and get your name on the list, and then we'll arrange a tour. Because it's always fun to see this in person. It's more fun than seeing it in a video, I think.
I do want to thank Dr. Admiral as well, because he's working on this project. He also has another project with Dr. Dvorak looking at sediment distribution in our stormwater runoff in MS4 communities. He is also working on one that should wrap up, I believe, this year. It's looking at
Yeah.
the stream bed stability, and there's a couple different locations, but one of them is just downstream of Spencer Dam because we had the failure in 2019 and we're trying to figure out when that stream will stabilize. So he has a lot of interesting things that have been going on for the university.
Thank you, Julie.
Well, thank you, and thank you for all of you to attend the webinar. We will be, excuse me, I will be following up with the PDHs at the end of the presentation. Well, thank you very much, and then I would just have a good rest of the week. Thank you.
Thank you, Dr. Admiral.